because the topic today has been rediscovered many times and with different names. Right, and I won't write this long name again. From now on, it will just be PS slash sum of squares. Yep. SOS-proof systems, and we'll also see connections to polynomial optimization, or semi-definite. So these were discovered in 3 different communities, 3 different times, but the underlying ideas, I think, start from the beginning. So let me start with some history, because it's kind of nice. It starts with this paper by Hilbert in '88. So who showed that the basic question was asking was, when is a polynomial always non-negative? It should be obvious. Okay. So when is a polynomial non-negative? Well, one simple case is if it is a sum of squares of other polynomials. And the basic question he asked is this always necessary? And in this paper, he actually showed something nice, which is there exist degree 4 3-variable non-negative polynomials that are not sum of squares. Okay. So what do I mean by this? There exists a polynomial p, which is from R3 to R, degree 4, and so if you take any finite number of polynomials and take the squares, you cannot recover p from them. Okay, and this was what he did, and he also gave examples, not examples, but such existence of such polynomials for every other cases, for every other even degree and more than 3 variables. And this was an existential result. He just showed that there exists such a polynomial using some algebraic geometric techniques. And he asked the following question, which which was his 17th problem in his address, which is Hilbert's 17th problem. So there is one other case where a polynomial can be easily seen to be non-negative. It is the case where it's a sum of squares of rational functions. Okay, so if p is summation I of pi of x squared by qi of x squared, okay, then it is clearly non-negative. And then Hilbert asked if this is a necessary condition. Okay. If let's say QIs are, let's say QIs are never 0. Yeah, that's also true. And now, so Artin in 1927 showed that yes, every non-negative polynomial is a sum of squares of rational functions. Okay? And what we are going to do today is kind of builds on this theorem and tries to get extensions of it which are suitable for optimization and so on. Okay? So this result basically started this area of, the first results in the area of real algebraic geometry, and later on it was developed into what is called positive Stellensatz. So before doing this, let me first revisit the classical null Stellensatz, which is let's just for comparison write it down. I think this is much better known than positive Stellensatz, and it says that if let's say you have some algebraic set, meaning K is a set of all x, which are solutions of some system of polynomial equations. Okay. Then K is empty if and only if there exists G1 through Gm polynomials such that summation I fi gi equals 1. Okay. So this is again clearly a sufficient condition. If there exist such polynomials, then all of these the FIs cannot have a common 0. Okay. And it also says that it's a necessary condition. Right, exactly right. I should write it down. Over algebraically closed fields. But this condition is extremely important because, for instance, the polynomial 1 plus x squared equals 0 has no solution over reals. Right? So the question now is whether you can get such a nice analog for the real fields. Okay? For fields which are not algebraically closed but have such orderings. And this is where positive Stellensatz comes in. There are many versions, and let me write down the simplest version, which is by Krivine, 60s, and Stengel, 74. This is now over the reals. We'll see. Yeah. So let's say you have the same collection of equations, but now over the reals. Okay? So x belongs to R to the n, fi of x equals 0. Okay. Then the positive Stellensatz result of Stengel says that, or Krivine says that K is empty if and only if you have some identity that looks similar. You would ideally want this, but also you allow sum of squares of polynomials. Okay. Once again, this is a sufficient condition, right? Because if there exists such a relation between the FIs, then they cannot obviously have a common 0. If there were a common 0, then you get 0 on the left-hand side, and you get a positive quantity on the right-hand side. And it's a very powerful result because it's saying it's a sufficient necessary condition as well.
So okay. Do you have any intuition why here you're allowed to use just polynomials instead of rational functions? So ideally, if you have summation fi gi equals 1 plus summation.
Well, there's a version. This is kind of. I think it's mainly because you're looking for the equations fi of x equals 0. But if you just ask for inequalities like p of x greater than or equal to 0, then once again you get rational functions.
I see.
Implicitly.
Because that result is telling us that R
Right, right.
polynomials that can't be
Right, right.
on the other side. Of the
Right. So this is for equalities. It's a good point. We'll get to inequalities, and there you'll definitely have these rational things appearing. Say that again? Yeah. As long as the field has some something called there's a technical no. It has to be ordered. Yeah, real closed fields or any field which is has some nice ordering properties. So there's a definition of pre-ordering over the reals that you have this less than or equal to relation. And there's an abstraction of that which I don't exactly recall at the top of my head, but it's not too complicated. I mean, it's something natural that you would probably come up with. Okay. So any field which has such an ordering will satisfy these things. And in fact, the proof of it critically uses that. It starts with the reals, and then you lift it up to close it, but still have the ordering and do something like that. So this is the simplest form, and as Ankur said, when you have inequalities, you still get some rational functions kind of thing. This is just the equality case. So let me state a simpler case of the situation where you have inequalities. That still won't get what you're asking for, but it suffices for everything we're going to discuss. So this is Putinar's PS. This is from 93. So, but apparently these three papers had some very important bugs which are only fixed like in 99 or something. So that's a small caveat. And so his positive Stalingrad is kind of very nice and suitable for computer science applications for the following reason. Okay. So let's say you're not just interested in equalities, but also on inequalities. Okay, if I don't mention where the indices range over, just think of them as any finite range. And so let's more generally say if now we will not just study when this set is, the semi-algebraic set is empty, but also when a specific given polynomial satisfies certain inequalities on over this set. Okay. Let's say I want to say that p of x is greater than or equal to 0 for every x belonging to k. It's almost the same, except that the formulation we'll have some conditions on k which make it nicer. You won't have any conditions on p. Okay. And right. Power of the other. Exactly. That's the right. That's the same thing, you get the same issue here. And Artin's theorem is kind of a situation where k is the set of all real numbers, or set of Rn. Okay? And Putinar's PS says if, okay, and k sat k is, say it's called, there's a technical condition called, k has to be Archimedean, but what it just means is that one of the inequalities, Gj, is of the form okay, again, this is a relaxation. You don't exactly need it to be of this form, but this has to be derivable from these guys. It's some kind of compactness condition. It's slightly stronger than boundedness, that you want the boundedness to be explicitly mentioned in the set of inequalities. Okay. So you want your set to be contained in some big ball. you know, forget for all of our talk, you know, for this entire talk, you can forget about this. Everything we'll study will be Archimedean. Okay? It's just a technical condition. Then subfields or extension fields. You can take extension fields of R. By let's see.
So you still need an order relationship.
Right. So you extend the way Artin's theorem is proved. In fact, is you find some non-negative polynomials and you can extend it with you can extend the reals with that polynomial, and then that defines an ordering. So technically, ordering is just like a convex cone, which specifies, then you say, you know, A is greater than or equal to B if A minus B belongs to this convex cone. So then you can extend based on these cones. And so the condition here, as you can guess, is so you have a sum of squares and then something in the ideal generated by the equalities, so which looks like what we have there, plus some sum of squares of the inequalities. Okay. So this is Poutinar's positives and such, and if you don't have this Archimedean condition, you'll basically have to look at powers of Gj here. Okay. So there's a description even for that case. Each of the polynomials is a sum of squares polynomial.
The polynomials by which you multiply Gj.
Right, exactly. Right. So SOS just denotes sum of squares of polynomials.
Rational functions or
Just polynomials. Just polynomials.
Anyway, so I mean, we can put this positive Sellenthal more on the same footing as the others by asking it for P is the one polynomial.
Right, exactly. Yeah.
So then it's telling you the condition under which
This set is empty
the set
and
is empty.
right.
Which now,
like, you know, you can ask for contradiction. Like, let's say P is -1.
okay, so the only difference between this and the like Stengel positive Sellenthal is
The inequalities.
yeah,
That's the
you're allowed
biggest
to
difference.
have sum of squares, sums of inequalities.
Right. And this Archimedean condition is kind of necessary too, because you can cook up some pathological cases where you do indeed have to look at powers of Gj and not just Gjs. Like, you know, you cannot derive, or we'll get to that in a little bit.
The original one, this is a strengthening of the original one where the part in which you take inner combinations of the inequalities you need to multiply by product.
Right.
Not just part.
Mhm.
Product
Okay.
of this.
Right. Like, for instance, if you
It's not just linear, yeah, making it linear.
like if you take this set K, okay, and then x is greater than or equal to 0 for every x belonging to K. Okay, but you cannot write x as a linear combination of the inequalities. You have to multiply some, you get some annoying technicalities and so on. So you'll get some products here. That's where the rational thing. So, yeah. You'll get P times something, and then you'll get products here. Yeah.
So the old one where A is equal to set, right? So
Mhm.
that's like P of x being, as you said, -1, for example.
Right.
So then down, and let's say all the GJ, basically there are no GJs.
Right.
This is equal to 0.
Then you exactly get the one
No,
before.
but now this becomes negated. The sum of fi, hi prime.
That's fine, right? Because these are just equalities. There is no constraint on the sign.
Just
It's just zeros. It's something in the ideal generated by the FIs.
Oh, okay.
So the case with equalities is much nicer. Okay.
But there's no Archimedean constraint. Like even if what
Right.
I said, it's still not the same as that because that is exactly.
Right. For equalities, you don't need any conditions. It's nice. But inequalities is a good case too, and we'll see why. And
But I guess I'm a little bit confused about something. So, I mean, here for this Putnar's positive self-test, you have a polynomial, an arbitrary polynomial in the ideal generated by, well, I guess it's not really an ideal because it's a semi-algebraic set. But,
right.
I mean, in general, you need, like, the radical of the ideal. So
Right, right.
This doesn't come up here.
No, no. As long as it's Archimedean, you can always find such things. Yeah. It's a powerful statement. Otherwise, you can. I mean, I'm not sure how much harder this is to
So
prove.
Archimedean, I mean, it's not true for, I mean,
No, no.
and,
This condition. I mean, how would you formulate even this condition?
Does not in particular explain that.
No. Well, maybe if you dig into it, there might at least not as a
not superficial.
not superficially. Yeah. Yeah. We'll get to that in a little bit. Yeah, that's the motivation. Yeah, you're jumping a bit ahead. Okay. So, but before going on, this is, I mean, this is a very cool result, I think, and so there are lots of other questions which are open, especially quantitative questions, and let me just state a couple. So, like, you know, how many terms required? Okay. How many terms required in Artin's theorem? And this is like mathematicians care a lot about this apparently, and they have very weak bounds. They have a lower bound of n and upper bound of something like 2 to the n, and also what degree bounds? So for instance here, what degree bounds can you put on the GJs, okay, on the HIs and so on?
With the null self-test, the degree bounds are
Right, right. I mean, like, there are some lower bounds and there are some upper bounds.
so the positive self-test is not understood, but the null self-test.
Not completely understood. I mean, there are some, like, you know, it's much better understood than the how many terms part, but it's still like, you know, I think even in the null self case, it's not completely understood. Right? There are some gaps. Okay. And now let's get to Andy's question. And so the reason we are looking at these because polynomial optimization. So what I mean by this, so I want to solve problems of the following form. Or so I want to solve problems of the following form. Minimize some polynomial over some semi-algebraic set. Okay. And this is a very powerful framework. I mean, you can easily see that it's NP-hard. For example, let's say max 3 sat. you'll just say minimize summation equals 1 to m of So if you have a clause of the form xi, yi, zi, you introduce this term in the expression. It just captures when this clause is satisfied. And then you look for minimizing this over the set of, or the Boolean cube, which is just x such that xi squared equals xi. Okay. So this is a semi-algebraic set, and this captures Tseitin. So it's obviously NP hard, and it's also much more powerful. And but we have some kind of guarantees that come from positive Tseitin. So let's see what they give us or what they suggest. Yeah, you can kind of embed all of these guys into just one polynomial as well. Like, so that, it's 0, if the minimum is 0, if and only if it takes an integer value. Like,
I think the problem is easier if the number of variables is that.
Right? Yeah. Like, for instance, I could just say plus I equals 1 through n of okay. So if there is a satisfying solution, then this will be 0. If not, it won't be 0. Okay. So even minimizing a single polynomial equation is NP-hard. You can make the degree even to be 2. Okay. But so let's get back to this question, and let's simplify and say we just have equalities. The case with inequalities is you run into some technicalities, but let's ignore them. Okay. So by positive Stellensatz, what do we know? So this says that the minimum is greater than or equal to lambda, implies so if the minimum value is at least lambda, then you get such an inequality that is satisfied over the set K. Okay. So now let's look at this decision problem. Is this polynomial non-negative on K? Right. By Putina's positive Stellensatz, we know that this happens if and only if P of x minus lambda is let me use J here. Okay. So this minimum is at least lambda if and only if such an identity holds. Okay. This sounds too good to be true, but
the f sub I has to be a sum of squares.
no. These are just the equalities. Okay. So the inequality case is similar, but let's ignore. Okay. And this sounds very nice, but the problem is we don't have any bounds on the degrees of these polynomials. Okay. So even if getting a bound on the degree of these polynomials would be a big result, I mean, it should not be true, because even if you can't find such polynomials, just knowing their existence would give you a certificate and so on, which contradicts some complexity assumptions. So you should not expect to have a universal bound on the degree of such representations. Oh, yeah, you can expect the number of variables and the degree of the equations raised to the n. Yeah, I should have written it down. Yeah. there's a bound of in Putinar's thing, the degree is less than or equal to max degree fi O of number of variables. Okay. It's for equalities. Oh, you're saying why doesn't?
So why can H
Oh, Hilbert's examples won't be Archimedean, and it's also for equalities, right?
but is K Archimedean? Why is K Archimedean here?
Because if you
If you didn't add the constraints explicitly, so
Right,
K,
right.
it's just implied.
if it is implied, yes. I mean, as long as you can derive it by linear combinations, you should be fine.
Because here it's only equalities. You don't have any.
So to be more precise, actually, even here you need compactness or Archimedean. So Hilbert's theorem, you don't have
Here I presume it's the
Right.
Boolean cube, so you're fine.
right. In general, you need Archimedean.
But Archimedean, it's enough. It's
Archimedean, or in the case of equalities,
no, that's what I'm saying. What I'm assuming is so you don't declare somehow.
well, the constraint that summation xi squared is less than or equal to r, will implicitly assume that it is there, okay? But you don't need to explicitly add it as long as you can derive it. Okay.
You can.
I'm assuming that it is. You can derive it. More technically, the actual statement should be that this set K should be compact. Okay. So in Hilbert's case, it's not compact. Yeah. Okay. So this is from the real algebraic geometry side, but let me now get to optimization. So this was an observation first made by Shore, and this is a different Shore. Right. And Shore. He made this observation for the unconstrained polynomials, and this was then discovered separately by Nesterov in 2000, and then Lazare in 01. Different papers. They're all different years, so I mean, there are minor differences, but I think the core observation you should attribute at least to maybe Shore because he was the first to do it. And the core observation is the following. I mean, the fundamental fact here that we'll exploit repeatedly is the following claim. There exists a polynomial time algorithm to check if a given polynomial P is a sum of squares. Okay. So let's say I give you the coefficients of this polynomial P. Okay. Then I can, in polynomial time, check if it's a sum of squares of other polynomials. Okay, that's the fundamental fact that we'll exploit a lot. Oh, sum of squares is for reals. And sum of squares of polynomials. Whenever I say SOS, it's just for polynomials. Never for rational functions, unless I explicitly, never for rational functions. Okay. Yeah. You need to polynomial in the number of coefficients of P.
Alright, so now just we need some other parameters, otherwise it's contradicting.
No. It's saying that if a given, you can check if it is a sum of squares. It doesn't say it is a sum of squares. I can verify whether or not this polynomial has a sum of squares representation.
No, but the sum,
If it doesn't have a sum of squares representation, it will just say, okay, it doesn't have a sum of squares representation. That's all. It's just a verification algorithm.
Not testing positivity.
No.
Whether it's sum of squares or not.
That's actually not true. I'll get to a bit. There is some, like, there's a way of rigorously defining the notion of a random polynomial. You have to be a bit careful because it's some continuous set. You can define some hard measure with a set of polynomials of certain degree. And there you can show that random polynomial is non-negative. A random non-negative polynomial won't be a sum of squares. There is such a result. Okay, and we'll get to finding explicit examples in 5 more minutes. Huh? No. You define condition. Yeah. You have to define the distribution carefully and okay. No. Like, it's NP hard, right? Yeah. So let me show this proof because it's very simple and you can see why the next part comes in. Okay. So maybe I should have written the claim here. Let me write it down again because I'll keep this up. Okay, so I'll prove that claim. It's actually a very simple but powerful observation, I think. So proof is so let's form this matrix. Okay, given P, we're going to form this matrix where rows correspond to monomials. Okay, that is, expressions of the form x1 to the I1, x2 to the I2, so on to xn to the In. Okay, and columns also correspond to monomials. Okay, and if we call this so the entry here, okay, m of I comma j will just be coefficient of okay. So I'll read it again. So you just look at the monomials. The rows are indexed by monomials. The columns are indexed by monomials. And the ijth entry will be the coefficient of the product monomial in P. Okay. And it's straightforward. I mean, you just write some calculations, and it turns out that P belongs to SOS if and only if M is positive semi-definite. Okay. So P is a sum of squares polynomial if and only if this matrix is positive semi-definite. Okay. And this is easy to check. Basically, one direction is given P, which is a sum of squares, you can directly derive, show that M is positive semi-definite. And if M is positive semi-definite, you look at its factorization and then rediscover the sum of squares representation of P. So now we know that checking whether a matrix is PSD or not is polynomial time. So you get the claim. Okay. So that's where the connection to semi-definite programming and semi-definite hierarchies comes. I think there is some work, but I'm not sure. I haven't looked at it too much, but I don't think much is known. Yeah.
So in the univariate case of this, I've seen this proof horizon, what's called the moment problem.
Right.
Trying to figure out if I give you a set of moments of
Right. Right.
Does this solve the multi-dimensional moment problem?
It almost does. I mean, there's actually parallel. I forgot one more thing in here, which is the moment problem, the classical moment problem. So there also people looked at these questions.
But does it solve the?
It almost does. In fact, Puchinar's thing gives a solution.
Almost.
Again, there are some technical conditions, like moment problem.
Field or on the.
So in moment problems, people like at least math community, they study it like when is the distribution completely determined.
No. I only care about is there.
Yeah, then this solves it.
So there is a multi-dimensional random variable that can only
There might be some technical conditions. I'm not sure. There might be some technical compactness conditions. I'm not sure. But that's where Putinar's thing also was used. No.
Yeah, so the input is the coefficient of the function.
Right. So if the polynomial is sparse and
Yeah,
Maybe exponential.
then maybe exponential. So basically, Shor then used this observation to study an approach, to suggest an approach for solving univariate polynomial, unconstrained polynomial minimization problems. Okay? But we'll study the more general case, which was done by Lazare. And this was again done separately by Perillo, but we'll follow Lazare's approach. Okay. So I'll slightly rush through this, and his approach was, let's look at this following sequence of semi-definite program. Okay. So let's say his approach was more or less to so look at that condition where we said it has to have a sum of squares representation of that form, right? But just put a degree bound on the fj's and the gi's. Okay. Now when you put a degree bound, there is a polynomial time algorithm for this, which grows where the exponent grows with the degree bound you put, right? And so you get a sequence of relaxations or better and better approximations, right? Okay. And oh, same.
Now we are not trying to change the sample without square, we need the
Right. So you can just put this inequalities. This will be an affine constraints. You'll have some affine constraints, and some matrix is PSD. Okay. So it's still a semi-definite program. So you get some thing which depends on the degree d. Okay? And what Lazare basically showed is that q star of d goes to optimum. For large enough. He had some quantitative bounds on how good you want the degree to be in terms of how good an approximation you want and so on. Okay. He had some technical things.
So the question is there a bound after which we know it is like?
Right, because Putinar's thing itself has a bound. Right? Yeah. And he also actually, this was not his original thing. This was his dual problem. Okay, this is the dual laser SDP. There's a primal version which I won't describe, but he actually studied the primal version mainly, and then he looked at the dual, which comes from positive stellar stars, and what he showed was strong duality holes. I think that was his main technical contribution, but let's not go into that. And so this is the familiar laser hierarchy that we study for combinatorial optimization problems. It more or less captures the same thing, but what we usually study in terms of vectors and like local distributions and so on corresponds to the dual of this optimization problem. More or less, within some constants, and I mean, he'll actually be starting looking at the primal, but for constants, it's fine, up to constants. So let me now, in the remaining 10 minutes, talk about proof systems. So this is PS proof systems. So these were first introduced by Grigoriev and Olabjar in '99. So in a funny way, they prove lower bounds for laser hierarchy even before laser defined them. So they come from the proof complexity world, I guess, and their interpretation was the following. Let's say I want to show that K is empty. You have some K which is just X such that Fi of X equals 0, okay? And I want to show that this is empty. If we want to show this is empty, it's equivalent to saying that the set of axioms Fi of X equals 0, if you treat them as axioms, then you should be able to derive a contradiction from them. And what kind of contradiction? So you want to get a contradiction of the form Fi Gi 1 plus summation J H I J square. Okay, so this is just positive stellar stars barring some technical conditions on these Fi's, and so they call such a refutation a positive stellar stars proof that this system of axioms is not satisfiable. Okay. On the Fi's, you need compactness of the set. Okay. So both cases, I think you need compactness, and one case you need even the stronger Archimedean properties. And so this is such an identity is a PS proof. Okay. And then you can extend it to inequalities as well. And they introduced this, then they studied what lower bounds you can show for such proofs. Okay. So if degree lower bounds, right? And their goal was basically what degree lower bounds can we show for such proofs. Okay, and morally, if you get such a lower bound, you also get a corresponding lower bound for the laser hierarchy, okay, which is one of the most powerful optimization techniques we know. should mention that like this is very powerful. This simple observation is extremely powerful. Okay, and I'll show you one example of it, or two examples. Right. Right. So there's like null strengths proof systems. There's polynomial calculus. There's like you can draw a diagram how it relates to everything. I don't think everything is well understood actually. So let me do two examples that this is powerful. I'll show two upper bounds, and then state an open problem. Okay. So I want to look at SOS proofs. So what do I mean by this? Like you have some identity that we use all the time, but now I want a proof which looks like that, like you express it as sum of squares. So let's do an example. The first example is Cauchy-Schwarz, which is probably I think the core example that most people will use. So it says summation ai whole squared is less than or equal to n times okay. So everyone knows the proof of this. This is just Cauchy-Schwarz. You do something. But you can also, there is a sum of squares proof of this. What do I mean by this? This is equivalent to saying that this polynomial is non-negative, right? And why is that? In fact, you can write this as summation okay. So not only is it non-negative, but it's also a sum of squares of polynomials. You can just verify this identity, and this is how you usually prove Cauchy-Schwarz, and you also get the equality case for free. Sum of yeah. Okay. And there's a similar proof for arithmetic geometric mean, but it's not so clear. It's a bit more complicated. Yeah, you can. So you can extend it to right, with some expectation thing. So the form that I think most useful for us is, let's say you have some random variable, some domain, and you have some functions on the domain. In fact, I'm going to use this, so that's why I'm stating it this way. But you'll have to put absolute values, which it's annoying for. Right. So to avoid absolute values and so on. This is kind of the expectation version of Cauchy-Schwarz, and you can just derive this from here just by, you'll have BIs, but that's fine. Okay? And this also has a sum of squares proof. You can just expand it out as before. Okay? So in the remaining 5 minutes, I'll give a sum of squares proof of one extremely important inequality in analysis of Boolean functions. You should try the arithmetic geometric mean. I think that's a very nice case. Oh yeah, let me in the same line. Let me mention that Hilbert in '88 showed the existence of non-negative polynomials which are not sum of squares. But the first explicit example was in 1966. So there was a long gap in coming up with an explicit polynomial which is non-negative but not sum of squares.
That's something very simple too.
Right. In fact, it's called Motzkin was the first one. But the simplest example I know of is so this polynomial in 3 variables is non-negative but cannot be written as sum of squares. Is it? Oh yeah. Mm-hmm.
There's like a very nice elementary sort of derivation
And I think there's a dearth of such examples. I'll state it at the end. So I want to prove the following inequality in sum of squares, and think I have time for that, or yeah, 5 minutes. Okay. So the inequality I want to prove is the following. So let P be a degree D polynomial. Okay, and in variables. And I want to say that expectation of multilinear polynomial okay. So this is the inequality I want to prove, that the expectation of the 4th power of a degree D polynomial over the hypercube can be bounded in terms of the expectation, in terms of the variance. Okay. So over the hypercube, 1 minus 1 to the n. Oh, this is it's not q, that's 9. Yeah. Yeah, as long as it's even powers and so on. Okay, and so this is, I mean, I think this is an extremely surprisingly powerful inequality. It comes up in small set expansion, comes up in the proof of Kahn's-Kallai lineal, on the KKL theorem, and so on. D is the degree of P. Okay. So I'll just sketch the proof. I mean, the details are easy to fill out. Okay, but the basic idea is that there's a proof of this which only uses Cauchy-Schwarz. Oh, but before going on, let me a quick quiz. So if I want to express this as some polynomial inequality, what are the variables? So if I want to use it in this framework, so what are the variables I should write it as? Of P, exactly. Right, it's a little confusing, I think. So what we are saying is, let's look at this degree 4 polynomial, which is this guy. Okay. So this is a degree 4 polynomial in the coefficients of P. Okay. And we're saying that this is always non-negative. And I'm saying this also has a sum of squares proof. Right. Okay. What?
So X is explicit.
Right. Yeah. Exactly. So let's prove it, and the proof is by induction. And because you have to do induction, you slightly consider a more general version, which is we'll prove the following. In fact, if I have 2 polynomials, P and Q, then this is at most 9 to the degree of p plus degree of q divided by 2 times okay. So let's just think of a proof of this, and we'll see that the proof straightforwardly SOSs, sum of squared. Yeah. Okay. And the idea is you write p as let's say x1 times some p1 plus p minus 1. Okay. This is I'm collecting all the coefficients which involve x1 here and all the coefficients which do not involve x1 here. Then you write q as x1 times q1 and then q minus 1. Okay. So let's now look at what happens to the left hand side. So expectation of p squared times q squared is you'll get squares of these guys, and and believe me, if you expand it out, this is what you'll get. So
Sorry, I'm missing that. So P is x1
times some polynomial which depends on x2 through xn.
I see.
Okay.
Oh, okay.
I'm just separate.
Oh, you're not evaluating the polynomial.
No, no, no,
Okay,
no.
I see.
Okay.
Okay.
And if I expand it out, powers which have x1 to an odd power disappear, and the calculations come out something like this. Okay, you get some seemingly messy expression like this, but the nice thing is all of these guys have degree less than the original polynomial. Right? Like for instance, p1 has degree less than degree of p. Okay, so you can use induction hypothesis here. You can use induction hypothesis here. You can use induction hypothesis here, and here you apply Cauchy-Schwarz. Right, but you look at the total degree. You do induction on the sum of the degrees of p and q.
Wait, what has degree less than what? The p1 squared, q1 squared is degree less than p squared.
Q squared. P1 squared, q minus 1 squared has degree less than p squared, q squared because p1 does. Right. So all of these have total degree less than the original total degree, so you can use induction hypothesis. And here you apply Cauchy-Schwarz. Wait, wait. No. Yeah, you do double induction then on the variables too. Yeah, you're right. So you get all of these terms, okay, and then you use Cauchy-Schwarz here, and you get this is less than or equal to 2 times expectation of okay. So a times b, 4 times ab is less than or equal to 2 times a squared plus b squared. And that's Cauchy-Schwarz, for which we have a sum of squares proof. Okay. And then you group things together and apply induction. So that gives you a proof of this inequality, and you can see that the only kind of non-trivial step we used was Cauchy-Schwarz, which has an SOS version. So you get an SOS proof of hypercontractivity. So the 9 arises because you get a 3 here, and if you balance out the constants, that's what you get 9. 9 is 3 squared. I mean, so let's do one more step. So if I use induction, I'll get 9 to the degree of p plus degree of q by 2. Okay. And here I lose 1 in the total degree, right? And there's a by 2, so you get square root of 9. And things balance out. Okay? It's just some really elementary calculation. And so this is thing. And let me finish with one open problem, which is find an explicit so I want a explicit degree for polynomial so that SOS doesn't give a good approximation. So far we've been looking at non-negativity and proving things by SOS, but I want an approximation, meaning that max let me say yes. Well, it's constant, right? So if you go sufficiently high, then you get the
okay.
right. So I want to say that I want an explicit degree for polynomials, so that if you look at any constant number of levels of SOS, you don't get a good approximation for this.
But why degree 4?
Any constant degree.
All right.
Any constant degree, yeah.
Okay.
I think there's a degree root n and so on. There should be a degree 4 or degree 8 and so on. Okay. Yeah.
Why do you call that degree 4 and not AMGM?
Well, it's the same as AMGM, except that you can also get it from Cauchy-Schwarz, and I showed that Cauchy-Schwarz has an SOS-proof.
Wait, so why is maybe I'm getting at what you were saying. Cauchy-Schwarz, when I think of like the expectation PQ, like all those things ABCD, expectation ABCD is that minus expectation A squared B squared square root times expectation C squared D squared. So where's the plus?
Okay, then let's call it AMG.
No, this is it's a very simple SOS thing, right?
I'm just saying
P1 minus P2 whole squared is positive. That's all it is.
Yeah.
This is not even Cauchy-Schwarz. It's just a square.
I'm just saying that 4 times AB is less than or equal to 2 times A squared plus B squared.
It's not even Cauchy-Schwarz. It's just one square. Okay.
This one's
I didn't gather that it was correct. I'm just saying I didn't know why it's called.
Oh, okay. It's not Cauchy-Schwarz.
It has an SOS-proof.
It has an SOS-proof, yeah.
And then the second question is, so can you recover stable powers down?
I'm not sure. I mean, there is a bunch of stuff you can do, like Ran and his student Yuan have some proof of the higher order polynomial things, but Latala's thing, I don't know. I mean, even you'll have to look through the proof and make sure it's inductive and so on.
Or even for degree 2?
Even for degree 2, I'm not sure. Like even for this guy, it's not clear if I want the optimal constant here, then can let's prove.
We actually have been hoping to give a very different talk where we talk about new results about Lasserre, but we've been working for a few months, and all we managed to do is just maybe understand better the papers that we read as opposed to solve our problem. So maybe there'll be some other talk some other time. Before I erase this, let me mention that this beautiful proof is due to a paper that was in the last Foxhouse talk, I don't remember, by Boaz Barak and David Steuer and Kellner and a couple of other people. And the main reason not the main reason, but one good reason to give this SOS proof for this hypercontractive estimate is that the hypercontractive estimate is what's used in the integrality gap for sparsest cut, and what's proving lower bounds on the degree. Let's say if you work in some semi-definite hierarchies like Lovász-Schreiber or Sherali-Adams, there were known. It was known that you need that. Well, these are Hot-Vishnoi examples that I'm not going to describe even, but they are used in proving that some semi-definite hierarchies require many iterations or high degree in order to prove a gap. And this is simply not true for Lasserre. So Lasserre is a more powerful system. We don't know a single lower bound in the optimization world which is better than constant on the Lasserre hierarchy. I think that's a true statement. Somebody should correct me if.
I mean, we have some things for
Okay, so maybe we should talk about CSPs. Yeah, maybe we should talk about CSPs, right? So anyway, proving lower bounds for Lasserre hierarchy became an even more important.
I mean, we know lower bounds for CSP.
Yeah, I'll show actually. I'll show. Yeah, that's right. I didn't. Maybe it's more in the unique games regime where we talk about two variables. Sorry, that's what I meant. Yeah, so for two CSPs. So we want lower bounds for the Lasserre hierarchy. And as we saw, this is the same as proving lower bounds for positive Stahlensatzs. So we'll talk about proving lower bounds, degree lower bounds for positive Stahlensatzs. The plan was that Raghu will talk 45 minutes, and so this maybe will, yeah, maybe we'll go back. So I'll have to skip some cool proofs I wanted to show you. But we are again looking at just a set. We're given a bunch of polynomial equations, and we are trying to derive a contradiction using SOS. Namely, we want to prove that 1 plus h equal f, where this is a sum of squares, and that will show that this set of polynomials is contradictory. And the question is, what degree can we do it? Well, so this is SOS, and this is in the ideal generated by these FIs. So we saw that you know, by all these theorems, there is always a refutation like this. So we will restrict ourselves to working in polynomials of degree d. So here it means that this polynomial h is a sum of squares of polynomials of degree at most d. And here we mean that this, when we write it as any element here is just a sum of gi fi. We want the degree of these guys to be at most d. Okay. So what do we want to show? What do lower bounds mean? We want to prove that if we take h, which is a sum of squares of degree d, and we take f, which is generated this way, so that the degrees here are d, then we cannot get such an equation. We look for the largest d for which such a representation is impossible. Okay. So the question for which kind of sets here, for which families of polynomials, and I'm going to just talk about polynomial equations. So what we are getting, the axioms are just equations, there are no inequalities. For which axioms can we prove lower bounds? So one thing to remember is that even without this sum of squares part, it's a non-trivial problem. So even if for a second we say this is 0, so a contradiction would just be proving that an element like this is 1, proving a lower bound of the degree. This is already a non-trivial proof system. It's called the Nostalzas proof system. So there was a question about proof systems. I'll actually, because of time, I will not give a full history. You can ask me, Mark, again your question at the end. But the relevant proof systems here are the Null-Stahlen-Satz proof system. As a proof system. So this is called, Null-Stahlen-Satz. This was introduced in a paper of, I guess, Beam, Impagliazzo, Pitasi, Krajcek, and Pudlak. Again, I'll be very brief with the history, and then the the polynomial calculus, which is also called the Grobner basis. Basis proof system, which was introduced, introduced by Clegg, Edmonds, and Impagliazzo. And those two proof systems are just about, there are no inequalities. It's just deriving one as a sum of, deriving one as a polynomial in the ideal generated by the given axioms, the given equations, up to some degree. And these were just dealing with, there are some lower bounds, and we'll actually see them because what we are going to prove is lower bounds in a system stronger than it, because we are allowing to add the sum of squares. So finally, we have this positive Stahlen-Satz, which is, was introduced by Grigoriev and Borov. Yeah, so this was in 1999. And, excuse me? In the, you remember, Ran? So it's in the, this is around 2000, I would say. No, before, mid-90s, sorry. Mid-90s, yeah, both of them. They're very close to each other, like within a year. And right, so these are the three proof systems, and I'm not going to, so we define Null-Stahlen-Satz. Null-Stahlen-Satz is just expressing one as an element in the ideal generated by the equations. Polynomial calculus sort of went into the following guts of this sum, and was saying the following, maybe we need high degree to express one as an element of this ideal. Maybe we need to generate very high degree when we just express it in a sum. But actually, if we are just supposed to generate one from these axioms, which should be all zeros, maybe we can do it in lower degree if we do it sort of step by step. So if we just allow ourselves to just generate elements in this ideal in a sequential way. So what do I mean by this? We can always take as an axiom. So we are going to generate a sequence of polynomials, maybe, let's call them A1, A2, AT, which will equal the following F, in such a way that every AI is either an axiom, or AI can be AJ plus AK, where these are JK less than I. So just in the usual proof system method, you generate things from the things you derived already. So the semantics is just that all these things are supposed to be identically zero. You start from axioms, so they are all zero. You add two of them, you still have a zero. And finally, you are allowed to take AI to be some variable, let's say x r times aj, again, j less than I. If you take a zero and multiply it by a polynomial, then you still get a zero. And the idea that if you do it like this, you can do in the middle degree reductions and somehow generate things in smaller degree than than you would be otherwise if you write explicitly everything. Now, I had the examples to give you. Let me not give you examples, but tell you that there are simple tautologies, simple contradictions, sets of polynomial equations, for which, if you, for which the, so let me call, I will have degree Null-Stahlen-Satz, degree polynomial calculus, degree polynomial Stahlen-Satz. And this is a minimal degree required in order to generate a contradiction in all of them. So each of them comes with some set of polynomial equations. So there are examples where, for example, degree, let me say that we will only be interested in sets of polynomial equations where of constant degree. So over n variables of constant degree. And there are examples where, for example, this is omega n, but degree of polynomial calculus, the same one is a constant.
So this is like Color's example, or like those types of things, like this, yeah, these telescope things?
Yeah, it's some telescoping thing. An easy one, if you just want log n here and 1 here, would be just a simple induction principle, which is x1 implies x2, x2 implies x3, x3 implies x4, and you want to derive x1 implies xn, or the contradiction that it doesn't, then if you do it this way, you have to sort of build a tree, and if you are allowed to eliminate eliminate variables, you can, I mean, iteratively, then it's very easy to do it in degree 3. So, so these are, of course, ordered this way. They become stronger and stronger. Here we allow this dynamic, this is the static version, that's the dynamic version, and here we allow sum of squares. So what we are going to do, what I want to tell you about is to, yeah, actually there is a sense, the question is what do you do with the sum of squares? So you're allowed to be dynamic on the equations in the ideal and static in the sum of squares. That's true. And that's all we'll do. So I want to show you two results. Both of them are due to Grigoriev, and they are in 2 papers from about 2001. Yeah. And I'm not sure which was which was the knapsack was later, right? Yeah. So this is the knapsack, and this is the. So here he proves that degree positive Stahlen-Satz of some, let me say, linear equations I'll tell you which one. So he develops a method for proving linear lower bounds on proving some sets of linear equations. And so I'll tell you in a second which ones. And here, well, let me tell you which ones. So we will see what they are, and we will see how to express them in a second. So I guess it will be interesting time-wise to see what I can tell you. But so we are looking at families of linear equations. The obvious way to represent them is, let's say we have some variables, Boolean variables. So we have yi, we have n variables 0, 1, and we have equations like y1 plus y3 plus this all exclusive OR, y7 is 0, y2 plus y3 is 1, and so on. So we have a linear system of equations like this. And we are asking, how much does it take to, what degree bound in positive Stahlen-Satz does it take to prove this, let's say it's a contradictory linear system. How much degree does it take in positive Stahlen-Satz to prove that it's a contradiction? Well, it's not obvious. We are talking positive standard just talks about the real field and you know, polynomials, and this is the G of 2 linear system. What do? You do the obvious thing. You translate it to the Fourier basis. So if you introduce, if xi will be 1 minus 2yi, then what this xi is 1 minus 2yi, then this would be, I guess, x1, x3, x7 is 0, is 1. And this would be x2, x3 is minus 1, and so on. Okay? And now it becomes statements about polynomial. However, we want to make sure that we are talking about Boolean values. So what we should add, so we have this family of polynomials given to us, plus the family xi squared equals 1, because we have the Fourier basis. These are plus minus 1 variables. So suppose I give you such a family of polynomials, these guys and these guys. What is the smallest degree in which you can prove a contradiction, assuming they are contradictory? It's very easy to prove lower bounds for when the statement you are proving is false. Okay, so what kind of systems are we looking at here? There are two sort of canonical things that people looked in the proof complexity world for a long time. They are canonical examples, and they worked very well for null standards and PC. In fact, they worked very well also for resolution and other things. They are the following. I mean, they play a very important role in the history of proof complexity, in particular for resolution. And these are the Tseitin tautologies, and random linear equations. So what are Tseitin tautologies? Let me tell you what are the in this language. Well, actually, let me tell you first what these are. So random linear equations. It's just let's say you take 3 lin. Let's say you take 3 lin. So it just means that each one, yi1 you pick these variables at random, 3 variables at random, and you pick this constant, 0 or 1 at random. And if you have n variables, then you would pick some constant, m, which is constant times n, appropriate constant, maybe 10n, and then, of course, there'll be contradictions here. So that's the random linear equations. That's one example, and that's one example for which this proof gives linear lower bound. Now, I should say that Schoenberg. Yeah. Weakest, the strongest. Yeah. So this proof system is the strongest known for which you have some linear lower bounds for this.
Is there what's the weakest proof system that does not get proved by random linear equation?
Well, if you are allowed, well, it depends what you measure in this proof system. So it depends, what parameter you are measuring. In this proof system, we are measuring the degree of a polynomial refutation, right? So in all these algebraic proof systems, we are measuring the degree. If we were looking at resolution, we would be measuring the size of the resolution, and this will be, what?
All of them are linear for linear equations. So is there a proof system where that gets that solves this problem with bounded refutation?
Yeah, if you are allowed to do Gaussian elimination.
Is that the only weakest one?
Yeah. But we'll talk in a second about what's behind this lower bound. So, but let me just mention that this is also due to Schoenberg. So it was proved separately after Grigoriev for Schoenberg. Actually, Grigoriev doesn't mention random linear equations in his paper, but the technique basically does imply it. Schoenberg, I think, independently of this, just proved it for random three linear equations. And the sort of importance of this for optimization is that you get here an integrality gap, right? Because what you're proving is that this cannot be refuted, so you cannot even prove that there is not a satisfying assignment satisfying all of them if your degree is bounded by, let's say, n over 10. Whereas for a random random assignment will satisfy half of it, right? So there you get this gap. What are the Tseitin tautologies? The Tseitin tautologies are the following. You take an arbitrary graph, and for some reason, well, for obvious reason, we look as the edge set to be n, because the variables will be on the edges. And you, so these variables y1, y2, y3. So you have this, and let's assume that it's odd. One can deal with even ones, but let's assume that the number of, v. Let's assume that v is odd. It can be m, and let's assume that it's odd. Then what you will require is that the sum of all edges, the variables of every edge touching a vertex, will be 1. So in this case, we'll have y1 plus y2, y3 is 1. And in general, for every v, the sum of ye, so that e touches v, ye is 1. Okay, this is a family of equations. What is the, why is it contradictory? Well, if n is odd, if you add all equations, you'll get 0 on the left-hand side and 1 on the right-hand side, right? So it's a contradictory system of linear equations, and you can ask, what is the minimal degree needed to prove it in this system. And again, that's what Grigoriev actually proved. He proved that it's linear if, so you have to add that G is an expander. So for expander graph G, you get a linear lower bound. In general, what you get, the lower bound you get just depends on the cut size in this graph, but let's assume G is an expander. So for every expander, this family of equations require a linear size proof. So, or linear degree proof. And let me tell you where this is coming from. So what is the source of the degree lower bound in Null-Stahlen-Satz, in polynomial calculus, and in positive Stahlen-Satz for these guys and for these guys? And that's a principle that sort of emerged from all the proofs in the on the lower bound proofs in resolution. It was somewhat hiding. I mean, these ideas were sort of hiding in the papers of Haken and of Zemeredi and Schwatal, proving various lower bounds on resolution for things like this. And Eli Ben Sasson and I realized that there were basically there is a parameter that tells you what to look at, and this will imply these resolution lower bounds. And it turns out they will imply also these degree lower bounds, and this is the width. So I have to tell you what is the width, or what makes a family of linear equations difficult. And this goes back to Gaussian elimination, to just adding linear equations. So you suppose you have a set of linear equations just like before. So let me write it as a matrix.
Wait, this notion of width also allows you to prove linear degree lower bound?
Yeah, yeah.
Well, it's
Yeah,
positive stuff.
yeah. I want to show you what's the width in a linear system, and that's why everything reduces to width magically. Yeah, I mean
So
you have
there's
to
a much simpler proof
say
of, like Grigoriev's results?
Grigoriev proves it like this.
I see.
He proves it. He doesn't write it quite like this. What?
I mean, he reduces it to the calculation of width.
Yeah, he reduces it to the calculation of the width. So I want to say what are the, you know. And you have this. So you have this system, and it's contradictory. So you know you can add a subset. You can find a subset that you. What does it mean that the system is contradictory? You can take a subset of equations, add them up. The left side will be 0, and the right side will be 1. That's the only contradiction you can have. And then what's the width? So this is a linear system. So width of L. So all of them are of this. All the ones I described are of this form. What's the width of L? It's so think of this as a proof system. Of the following as a proof system. You're just allowed to start taking. So you're allowed to generate. So not A. So whatever. That's L and M. You're allowed to generate M1, M2, MT, okay, which will be 1. That will be the contradiction. So you're allowed to generate linear function, linear equation, well, just linear functionals, so that MI can is simply. So M1 is well, maybe this is 0. Okay. Mi minus 1 plus some Lj. So you just start from the 0 equation and just add equations till you get a contradiction. You prove that 0 equals 1. Very simple. That's the simplest proof system one can imagine. Actually, it was explicitly suggested by Alechnovich as part of. Yeah, I guess it's not written explicitly anywhere. But anyway, it's an extremely simple proof system. And what is the measure? What is the cost of such a thing? The cost of such a thing is simply the width. The width of this proof is simply the maximum size of any one of these linear equations. So you are somehow trying to add linear equations, but trying to make them as narrow as possible. Yeah, so if you want, think of them as affine functions and keep the constant. Yeah, with the constant, yeah. So what's the smallest width? And as it turns out, this width will dominate all the lower bounds that we are going to talk about and all the many others. And how do we see that this width is large? Yeah. Yeah, they are all. They will all have, like random 3-lin. It will be 3. In graphs, you'll take bounded degree expanders like the 3, 3. It will be 3 again. So it's in almost all of proof complexity. It makes sense to start from like 3 sat, and in fact, you can always reduce to 3 under general conditions. So yeah, you start with small. So the width is not introduced because you have a huge linear equation in there. Yeah.
So why is width the right parameter and not the length? Or so if there is a small degree or degree for that matter, if there is a small degree proof, then you can find it easily.
So here's the reason is more or less the following. It depends on which proof system you look at. It turns out that the width is relevant to to resolution, because in the same paper that I mentioned with Ellie, we proved a theorem like, of course, it doesn't talk about linear equations, it talks about disjunctions, but the story is exactly the same. Prove something, the title of the paper was short proofs are narrow. So if you have proofs which are not too long, just the normal size of proof, the number of lines in the proof, if you have a short proof, then it's also narrow. So it also implies a low width proof. So width lower bounds implies size lower bounds in resolution. And what we will see, and here, what we will see is that, at least in the two examples that we, well, not the two examples, sorry, for linear equations, for this side of Grigoriev, we'll see that width implies degree. And there's one insight there that Grigoriev already used when he was proving lower bounds in the polynomial calculus, that I'll explain, which connects width and degree. Okay.
How is degree connected to length or difficult to find?
That is two different questions. So degree is not directly connected to length. If you are talking about the dense representation of polynomials, then then it's proving degree lower bounds and size lower bounds are the same. If you're explicitly asked to write a vector of coefficients, then it's the same. Otherwise, we don't know. Otherwise, degree lower bounds are not the best you would like. You would like actually size lower bounds, and we don't have them in general. Now you ask what?
We don't have any size lower bounds.
We don't have size lower bounds. And for your other question, for these proof systems, and in fact, Raghu showed you even for this proof system, if there is a short proof, you can find it, right? Because the semi-def. So here it was a Grobner basis algorithm. Here it's you need a Grobner basis plus semi-definite programming. So it's what these proof systems are what's called automatizable. If there is a short proof, you can find it efficiently. This is not the situation for general proof systems. We don't know it, and in fact, we don't expect it for strong proof systems. Yeah, yeah. So if there is a proof of this type, you can find it, and it's a Grobner basis algorithm specialized to the case where you have Boolean constraints. Yeah, then you can always find it.
Your paper with Ellie is based on taking a proof which is short and compressing it down so that the width is also small. And what about in the sort of Grigoriev stuff? So if you had a dynamic proof which didn't have too much size there,
we don't know how to. Yeah.
Hope?
So there is a in the dense representation to prove that degree and width.
So
the size.
Size of a polynomial in its dense representation.
Mm-hmm.
Then okay, that's what you're asking.
Yeah, yeah. So let's just talk about degree lower bound. Let's just talk about degree lower bound. Maybe we'll discuss size later. Right. So what makes width large? How can you certify easily that the width is large? I claim the following is. I'm not going to prove it. Again, I was planning to prove it, but the idea is that if you have large subsets, if for every large subset of the linear equations, when you look at just this submatrix, so there are ones at 0, 0 representing the linear equations. If there is a submatrix which has sort of an identity, so there are lots of variables which appear uniquely in their columns. If for every set which is linear, let's say, linear size, when you look at the submatrix spanned by it, you find lots of variables which occur uniquely in a linear equation in this subset, then this will give you a lower bound on width. Let me sketch very, very quickly the proof of this. Is it clear what I'm claiming? Well, look at this proof system. What's happening in it? We keep adding linear equations, and eventually we reach a contradiction. In both these types of linear systems, both when we have random linear systems and certainly here where we have any connected graph, and these are the linear equations defined by it, just to generate a contradiction, you need many of these linear equations. Here you need all of them because you need the oddness. I mean, if you have one less, you just cannot generate them. So here you need all of them. And in a random set, you can see that, if it was not 10n, but n over 10, maybe there will be equations which are consistent. So you need the minimum size subset to generate a contradiction. Doesn't matter in which order you add them. The minimum size will be large, right? So let's say that we need omega of n equations for a contradiction. Now, each time you add, the number of, okay, so let me do it a little more slowly. Let me not do it, and because I will not get to the positive challenge. Just waving my hands. What happens in a proof system? You keep adding these linear equations, and you keep generating linear equations as part of the proof. Every linear equation you generate is derived from some subset of your linear equations. When you added them up, these variables have to remain there. So in the linear equation you currently have, you at least have, maybe you exactly have those that appear uniquely because you are adding mod 2, right? If for any moderate size subset you have many of them, it means that the width is large. So the only question is, why would you ever have to add many? Well, you have to add many because no small subset is generating a contradiction. So sometimes you have to add many. When you add many, the width of your linear equation is large. So this is a really simple width lower bound, and what it translates to here. So you just have to ask yourself, do I expect these patterns in my linear system? But if you look what this pattern is in the case of a graph tautology, a Tseitin graph tautology, well, it just, if this is a subset S, then these guys which appear uniquely are exactly the edges in the cut between S and S complement. And we know that in any expander, if these two sets are linear size, then this is a linear number of edges. Similarly here in a random, this is just, you look at it and think about a linear, random hypergraph, random three-uniform hypergraph, where you look at a subset of vertices of, I don't know, n over 10, there'll be a constant fraction of n triangles which are just stick out exactly like this. This is explicit. That's so in random you want to prove random. Yeah, you can give explicit, but you want to prove random because you say almost all linear systems require large degrees. Yeah. Okay, so these are the tautologies for which lower bounds are proved in this paper. And I want to say something about both papers. Let me just say what the is the tautologies that play a role here, and then we'll see something about the proof technique. And maybe I'll steal 15 minutes. I don't know if you, well, we'll so here's a very, very different type of tautology, and this is the following. So here we are going to work with Boolean variables in the usual sense of it, so 0, 1 variables. So here we are going 0 and 1. And so we add the axioms. So these are axioms. Here this says that every xi is Boolean. And we write here sum of xi minus r. So these are called knapsack tautologies. And why should it be, why should this be contradictory? The point is you take r to be k, which is an integer, plus epsilon, let's say, which is a number between 0 and 1. So the sum of Boolean values is going to equal some fraction. That cannot be. Okay? So let me just state results for k, which is smaller than n over 2. So it's certainly contradictory. What's the degree? And it turns out that Grigoriev, this was not Grigoriev. I think that in a paper of Bass, Pitasi, Bass, Impaliazzo, Grigoriev, and Pitasi, they already proved that the degree of a polynomial calculus, so we are not allowed inequalities, of these knapsack tautologies, so let me call this k sub r. So this set depends on r. What is this? Yeah. So degree of k sub r. So this is true for every r, as long as you, for every r. Okay, so the minimum degree is basically, I should say that whenever you have Boolean axioms, whether these ones or xi squared equal 1, wherever it went to, so whenever the variables have to be Boolean, then there is always a linear degree upper bound. There is always an n or n plus 1 proof system, which sort of is analogous to triangle satisfying assignment. You can implement it in essentially in any proof system. So this is sort of amazing, it just says that it doesn't matter what, if you try to prove anything false, it requires full degree, it requires degree n. And we may see this. Then Grigoriev, like we said, looked at the positive Stahlensatz case. And what he proved is that this is omega of k. Remember, r is k. So if you want to prove that it's at least, 10.1, then you need degree 10. Okay, if you want to prove that it's 20.1, it's degree 20. He proved this lower bound. Actually, he asked in the paper whether it's tight, because there's this, it doesn't quite.
What if you make a substitution like x sub I equals 1 minus y sub I?
K is less than n over 2. Yeah, otherwise you have the complement. Yeah, so you could flip. You could flip. You could, I could give a result for k bigger, but let's say. And it's a small observation that we made with Raghu and with Chris Beck when thinking about this thing, is that you can prove something like a 2k upper bound. So actually, it is, it makes a difference whether this number is 10.1 or 20.1 or square root n plus 0.1.
Does this have to do with you're only trying,
Let me give you just a quick illustration of why having a sum of squares makes a difference. It's a very simple observation. When you don't have it, you need degree n for any r, positive or negative or huge or small. But consider the case that R is simply less than 0. It's also a contradiction, right? And then you can write the following. So we already have this sum of xi equals R. That's an axiom, right? And let's add to it
So you
some.
just add the axioms directly, right?
That's also an axiom. So what do we get here? We get here that sum of xi squared equal R, but this is non-negative. Right? So in degree 2, you refute it, despite the fact that in Nullstellensatz or positive calculus, you linear degree. And then it turns out, I mean, if you, when R is positive, and it's, you know, it's somewhat this, it's interesting a little bit how the upper bound works, but I'm not going to show you. You basically shave off one by one, and you pay the degree. Okay, so good. So let me say something about proofs. Yeah.
It's a very simple rounding trick.
What?
It's upper bound is a very simple. Actually, not even O. It's like just k plus 1 using a very simple rounding algorithm.
First of all, we don't know k plus 1. I think we know just 2k.
Rounding algorithm shows k plus 1 is plus 2.
Okay, so maybe, yeah. It's not, I mean, it's not complicated, but it's sort of interesting. Yeah, we didn't know it anyway, and Grigoriev asked it. But yeah, it's not a big deal. It just shows that his result is tight, which is interesting. Somebody has to do something about this board, I think. Okay, so I want to tell you about the proof technique for both of these results. And I think the moral of the story is that being greedy pays. So when you want to prove these lower bounds, you just do what you have to do, and it works. So this is especially simple with hindsight after you read the paper that somebody already did it for you. But so what do we need to show? We need to show that 1 plus h is f, where this is the sum of squares, and this is in the ideal, so this is some gi fi. We have this set of fi's, which are the equations we get. So what do we want to show? That so we are going to restrict ourselves to polynomials of degree d, so this will be in SOS d, and this will be in the So, I mean, this method should be familiar also to people who've you know, thought about lower bounds of semi-definite hierarchies. You're trying to build an imaginary world which is consistent, in which you interpret every polynomial of degree at most d as a real number, as a number. Okay, and you just want it to satisfy, you know, what has to be satisfied. So what has to be satisfied? So we are looking for a map phi from all polynomials so let me say it, just polynomials of degree d, at most d. What should it satisfy? Well, we want the following. We want that, suppose just a second you know, if we are looking at the world before inequalities, also when they were working on Nullstellensatz and on polynomial calculus proofs, that's what they were looking at. So this didn't exist. You just want to show that in degree d, you cannot generate a polynomial which equals 1 from the axioms. So you want this mapping to be 1 on 1, and you want it to be 0 for every f in this idea. I mean, if we had such a map, then we just apply it to the left and right side and get a contradiction. Okay. So how more specifically are we going to get it? What's in this ideal? Well, if we can generate this map as a linear map, what are the steps in the, I already erased it in polynomial calculus, what are the steps? You either add two things that you have, right? Or you multiply them by a variable. Okay, so what you want, so we'll try to take this to be a linear polynomial. So where degree is at most d. And the other thing is that when we multiply things by a variable, we better have that if phi of f, I will not write up to degree d all the time. We just care about polynomials of degree at most d. If we already have this equality, and if multiplying by a variable still keeps the degree below d, then we want fj we want consistency. Okay, if we can have these two properties, then we are done. This is if we are if we have such a mapping. Again, if we have such a mapping, then for all polynomials of degree up to d, then degree d cannot generate a polynomial f here, which equals 1, because applying the map on both sides will give us 1 here.
Where does the degree come in the? I mean, so
Yeah.
do you really want this map phi to be 0 on all of the ideal?
No.
Or just the degree?
Yeah.
Is that the degree d ideal?
Yeah, it's all everything is the degree d. Everything that generates, yeah,
Okay,
yeah,
okay.
yeah.
So that's
This
fine.
is why it's local consistency. We don't, yeah, it cannot be. I mean, at some point it's false, right? Because we can refute it if the
So that's the degree d.
that's the degree d. Yeah, I'm just proving. Yeah, so this for some d, if we can do it for degree d, it means there are no degree d refutations like this.
No, but I mean, if you apply the mapping to one side, you get the x side, you get 0. But if you apply to the left side, I mean, you know that the mapping it maps to 1 to 1. But what about 1 plus h?
Yes.
No. So I didn't get to h yet. Yeah. I'm just ignoring. So far I said what to do without the h, and in fact that's exactly how people prove lower bounds for Null-Standardsatz and for polynomial calculus. That's what they do. They generate such a linear mapping. And what do they do if they have the h? Well, you better have the. So you add another criteria. You want to have phi of h squared for all h degree, maybe degree h less than p over 2. You make sure of this also. So
is
now
there-
how do you do it? Yeah.
Is there a way that I mean, that we can think about this also as the moment problem right now?
Yeah.
Like, by, like, finding.
It is the same.
I see.
It is the same. Yeah. So it's a solution to the dual. Yeah, absolutely. This is a solution to this. Okay.
Do you like a pseudo evaluation?
Yeah, it's a pseudo evaluation. Yeah, you want something consistent up to a degree d, which satisfies the thing that your proof system does, which is linearity and multiplying by monomials. Yeah, just something that preserves this. So what are these going to be in the case of knapsack and in the case of the linear systems? So I'll do it again quickly, but I'll explain. Okay, let me actually say for the knapsack first. So how would we build such a mapping? Well, let's look at the knapsack. We know that, so we need to give, I didn't say one more word, one obvious way to generate this kind of mapping is to define it on monomials and extend by linearity. So define phi on monomials. And monomials, I would look at just multilinear monomials. So this is the product I and I, xi. Just on multilinear monomials. Why? Because we have the Boolean axioms. They are actually different in the two results, and it's important they are different. But you define it for multilinear monomials. You extend them to general monomials just by replacing, in Wild's case, every xi squared by 1, and in the other xi squared by xi. Okay? So just you're basically working in the algebra, which is in the factor algebra when you reduce by the axioms xi squared minus xi.
Particular to the axioms that you have.
Yeah, so we are, yeah. So when you are working here, you reduce by this. So every xi squared is 1. When you work here, every xi squared is xi. So you define it just, in both cases, you just define it on multilinear monomials. Okay, so the question is how to define it on multilinear monomials. You need phi of 1 to be 1. We need phi of 1 to be 1. And well, we have to start thinking about our monomials. What are the first monomials? It's the variables, right? So how are we going to define phi of xi? And remember that this is a thing we know. Xi is R. This is the equation we know. If you think about it, this is the only axiom we have if we think of Boolean. So it's pretty clear that if you had any refutation of this system, you would also have a symmetric refutation, because this is a symmetric condition. You have just the sum of the xi's. If you had any refutation, you take all permutations of the variables and you get refutations of all the permutations, and you could add them up. So you'd have a symmetric refutation. So we could go this way and define symmetric refutation, but we don't need to. What it tells us is that for this dual problem, for choosing the functional phi, we better make sure that all of these are equal. So this will be just phi of, so when we look at xi, this will be some function of the cardinality of this set. For every monomial, every multilinear monomial, we will map it to a number which just depends on the cardinality. So in this case, it will be phi of 1. Phi of 0 is 1. So what should we pick to be the value of xi? So that we have this equation satisfied. We want to all these axioms satisfied. So it's clear that this should be R over n. Okay. What about second monomials, where we can multiply? We can look at sum of xi squared. This is R squared. But what is this? We open it up, and we get here sum of the xi, because xi squared equals xi, plus sum xi xj, I different than j. Right? But this is R. So what we get here, if I move it to the other side, we get R squared minus R, and our n times n minus 1 terms here. So we get phi of 2, which is phi of xi xj, is R minus 1 over n minus 1. And so you continue. It's just you are forced. If you want the property that, if you want this property, then you are just forced. You keep multiplying by variables. You open it up, and you see what value you have to take if you want this to be satisfied. So you are really forced. It's a greedy approach, and you are forced to do. So in general, you can see what part of this thing will be just n R minus 1. R minus I plus 1 over n minus 1, n minus I plus 1. Okay, so we are forced to do this, and nothing stops us from doing it all the way to monomials of degree n, right? So we have our, and then we extend by linearity, and we are already done with the polynomial calculus lower bound. We found a way. This goes up to monomials of degree n. So since we had such a function phi, this dual solution, we immediately prove, this immediately implies that the PC of knapsack for any R is at least n. So that's the Bassett R result. Now what about the H? How do we prove that this is, the mapping? How do we prove this? Well, it was already suggested when Raghu drew this matrix that, talking about the show result. What is a polynomial squared? A polynomial squared, if you just draw, we have evaluations for all monomials, right? So what is a polynomial? Right, for every xi here, every xj here, the product of these monomials, and remember in the knapsack case, we are the case that we have 0, 1 variables, so this will be x to the I union j, right? This is the monomial here. What happens when we apply phi to the square of h? We can expand h, so if h was sum of alpha I x to the I, then h squared will be sum over ij alpha j x to the I union j. Okay? So when we apply phi to this, when we apply phi to this polynomial, what we are doing is just evaluate. If we wrote just phi here, okay, we wrote phi here, and then we just so if this matrix is M, what we are looking at is M alpha transpose. Right? Alpha is the coefficients we have for the polynomial f. So what we want is this to be non-negative, and this should be non-negative for any polynomial. We don't know what the polynomial is, right? So what does it mean? So this will be implied, and effect is equivalent to M being PSD. So what you are forced to do is to think about this strange matrix in which these entries are basically this product, R minus 1. And think whether it's a PSD matrix. What Grigoriev does is just proves that it's a PSD matrix. It requires some work because it's a non-trivial matrix. We have some simplification of this proof, but I'm not going to show you. It's still not completely obvious why it's true, although there is some intuition. There is some intuition here. Because we are in the xi squared equals xi. For knapsack, we are in the Boolean case. Xi is a 0, 1 variable. Yeah, and you're right that when we do the other one, so let me just hint what you do in the case of the other one. But any more questions about this? I'm not going to prove it. Yeah. You can, but I mean, it's an asymptotic thing, right? You want to do it analytically.
Yeah, analytically.
Yeah, so you can.
Yeah.
Yeah, so
It's hypergeometric series.
yeah, so you can. You can.
Because of the symmetry, can you reduce it to a much smaller question?
It's not clear. Yeah, exactly. The entries of the matrix are not symmetric. But
you can symmetrize it so that the matrix is only the coordinates of I union j. So you can symmetrize.
actually, yeah, I think you are right, because at the end, it's a good question. I think you can. Yeah, but you still have to prove it. Yeah, but that's a good. I think you can symmetrize it, although that's not what we. What? No. Symmetric. No. what the question, Sushan's question was, having something here just depends, you know, this is an exponential size matrix. It's n to the d. Having it just d by d, d plus 1 by d plus 1. Yeah. PSDNS fails for k plus 1, absolutely. Well, maybe 2k. Maybe 2k. It's k plus 1? Okay. So yeah. You can, because there is a proof. So yeah, so exactly. This fails because the equation side doesn't fail. If you just use equations, it doesn't. Yeah, so it fails. In the other case, let me just show you what the matrix is, or what phi is without yeah.
So if it really was a distribution on the hypercube, then phi of a squared being greater than or equal to 0 would be d. Right?
No, it's a real. The coefficients are real. The coefficients are real values, and they can be positive or negative.
It cannot be a distribution.
It cannot be.
Yeah, it cannot be a distribution in particular, but.
There is a proof, for example. So then.
So let me tell you what happens in this, in the case of linear functions without proving anything. So we have things, the axioms here. The Fi is of the form something like the product of x I. So we have subsets, maybe they're of size 3 or size whatever. Minus AI. Well, this is a plus minus 1. That's how the axiom, that's the linear equation, right? So, as it turns out, these are much more general. There is a much more general setting capturing this type of axioms in which it is a difference of just two monomials. Okay, there's just a difference of two monomials, so mi minus ni, monomials. And these are called binomial systems. And sometimes they are called rewriting systems or 2S systems. And these are just what they tell you is that whenever you see a product, you can replace it with another product. So another way, so saying that this is 0 more or less says exactly that this is the same as ni. So if we were just working with multiplication, remember we also have, we also have this x I squared equal 1. If we were just working with multiplication, this will be the same in this setting, which is the same as xi equals xi inverse. This will be the same as saying mi ni is 1. Okay, so we are allowing something that's not in the proof system, but simply corresponds to the exclusive OR operation in the GF2 setting. Okay, so what I'm getting at is the following: the idea in the linear case is just to take these as your axioms. Here they already come exactly like this. They just come as product equals the constant. To just take this set of monomials, which are equal constants already in the axioms given, and just see what you can derive from them. So just, you're allowed to multiply them out and get other monomials that equal other constants and so on. So you're just going to get from just iterating, multiplying monomials and getting the, so okay, let me just say it like this. You just start by saying that, yeah, that's what we call x to the ij. I is simply ai. You start your mapping phi just from what's the constants given by the axiom. And then you just try as much as you can to do this. If you have already generated such a thing, to have, right. You try to make it multiplicative. I mean, you do make it multiplicative as long as the degree is less than d. This is just what we did with the linear systems. We are just adding linear systems as long as replace degree and width. You see that what is happening in this chain of implications is exactly what happened when we were adding linear equations, just written multiplicatively. So if we do just this, we don't add anything yet. We just do these multiplications. Then what we are doing is the GF2 operations. And as long as we don't exceed the width of the system, if we replace width and degree, which is just, I mean, we equate degree with width, we will not generate a contradiction here. So this will be a consistent labeling. This phi will be a consistent labeling. And so just from here, we are not going to get a contradiction. So that's fine. So the only last thing, the last thing on the board I want to put is why is it PSD? And that's something that's extremely simple. It's much simpler than in the case of the knapsack. So we have this multiplicative function. And notice that these are, again, these numbers are always plus minus 1. Yeah. So again, we have xi, xj, and here we have x I exclusive or j, right? And one thing I didn't say is that, well, there are a variety of monomials for which you get values, plus, minus 1, and there are others. Well, all others, so these are, you do it as much as you can. You generate all the equations within degree d or within width d that you can. And all others you declare, you simply declare 0 if L was not, oops, that's terrible, not generated in this sequence. Okay? It cannot be generated in width less than d. So all the others are 0. And so you look at this matrix, and what do you have in this matrix? 1s, minus 1s, and 0s. And the main claim, it's an observation which is really, really simple, is that this matrix must look like a block matrix where everything of the diagonal blocks will be zeros, and everything that's in every diagonal block is going to look like this. And what are the reasons for this blocks? Well, first of all, it should be clear that this is a PSD matrix, right? I mean, each one of these is a rank 1 matrix of what? Minus 1. Sorry, it's a symmetric matrix. Sorry. So each of them is a PSD matrix, so that's not a problem. Why does it have this structure? It has this structure because of this multiplicativity. So first of all, whenever things are defined, they are multiplicative. So I mean, that's, yeah. Well, whenever things are defined, they are multiplicative, and that's the reason for this rank 1 matrix. I mean, if you put here phi of x, if you put phi on the rows and columns, and this will be the product, then it will have this structure. So it's multiplicative, except when it's not defined. What you want to say is that it's not defined exactly in block structure. So you get exactly these blocks, and this follows very simply because for any three subsets of size at most d, when you look at x, I XOR j times, so phi times phi x j XOR k, because of this multiplication. if these two are defined, you could generate the third one, x, I. Okay, so basically what it says is that you have complete graphs here. You don't have holes. You will never get a hole. If these are non-zeros and these are non-zeros, you are not going to get a zero. You just get product. So anyway, I'm not doing it in any detail, and I should stop. So you get a PSD matrix, and that's why this mapping is good.